So this is work that I've done. I'm doing together with Jack Janssen, who's also at CWI. When Jack introduces himself at conferences, he says the thing of note about him is that he's the world's second Python programmer, and that's because Python was developed at CWI, and he was the first one to pick it up from here. So, 2017, an important milestone year, because it's exactly 60 years since the first municipal computer was ever installed. And we're lucky enough to have the photograph of them unloading it at the bay. This is the town hall in Norwich, where it was installed. In fact, this is just one of 21 boxes that had to be unpacked for the computer. It was a large thing. And then 2 years ago, this happened. Do you know what it is? Raspberry Pi Zero. Oh. Is that better? Good. Raspberry Pi Zero. General purpose computer. The first computer that was so cheap that they gave it away free on the cover of a magazine. Now, some wag at the time went and made this picture, which is the same building. Who here thinks that, well, I'd like to know what you think about which one of those two computers is likely to be more powerful. Who thinks that the Elliot was the more powerful computer? Correct? Oh no, two people. So the rest of you who thinks that this is more powerful, do you think it's 10 times more powerful? Who thinks it's 10 times more powerful? More? I don't mind. Whatever way you want. Anybody think that is more than £10? No. It's actually a million times. Oh God, what's happened here? Sorry about that. That is not meant to happen. So the Raspberry Pi Zero is about 1 million times faster. Which means that if they'd run the Elliot 24 hours a day for 10 years, it would have done the amount of computation that you can do on this in 5 minutes. So in other words, this, compared with the Elliot, is an enormously powerful computer. In fact, if you compare them, you can see the instruction time is what I was using here for a measure of power, but it's got about 1 million times the power, 500,000 times as much main memory, and so on. You can see all these details on the slides, which will be online after this talk. But what this means is that the Raspberry Pi, I should have shut off Facebook, I'm sorry about that. The Raspberry Pi is a million times better because it's 1/1,000,000th of the price and 1,000,000 times faster, which is a word that we call a billion in Europe and a trillion these days for the Anglo-Saxons. Now, a terabyte is 1,000,000,000, so it's a sort of number that we have to deal with every day. So I would like you to estimate for me, if I asked you to count the number of bytes on a terabyte to make sure that they were all there, for instance, and that you could count on average over a day 1 byte per second, how long would it take you to count a terabyte? Who thinks it would take more than a year? Correct. Who thinks it would take more than 10 years? Correct. Anybody think it would take more than 100 years? Yeah, it would take 30,000 years. 1,000,000 is a very big number. But in fact, 1,000,000 is what Moore's law would approximately have us to expect over 58 years. But in fact, the Raspberry Pi is even better than that because it's 1,000,000 times smaller as well. So it's really, in comparison with that first municipal computer, it's an absolutely amazing computer. So that's how we're getting the Internet of Things, because of these things basically being embedded everywhere. But the problem with the Internet of Things is that they're all producing different data formats, text, XML, JSON, goodness knows. They all need to be accessed. There are various ways of accessing them on demand, by push, so that you actually have to listen all the time, or they're stored in the cloud somewhere. And so if you want to make an application from all these Internet of Things, joining them together, it's a lot of hassle because you've got to do a lot of programming and a lot of conversion and lots of different access methods. Now, I should say the Internet of Things, although we're talking about it a lot nowadays, is not new as such, because even 20 years ago, a typical gas station, petrol station, would have had embedded computers in all the pumps, in the storage tanks, the tills, the vending machines, and these would have all been accessed centrally to give you the data. So Internet of Things is not per se new. What is really new is the ubiquity and, unfortunately, the diversity. And I should also say that the P in IoT stands for privacy. And the S stands for security, because Internet of Things is introducing loads of social problems. For instance, do you own the data? Can others see the data? And who is allowed to do anything with the data? These are issues that are not really settled and problematic at the moment. So what we are trying to do, and what I'm describing to you today, is a project where we're creating a system that allows you to retain ownership of the data, or to control who can see and modify that data, to hide those difficult data differences, data format differences, and the access differences, to integrate all that data in one homogeneous collection, and then allow the system to update itself and update the devices autonomously as necessary without you having to intervene. As a result, we could then use a REST-style interface to the collection to access the data, to change the data, and therefore to control the devices without having to worry about all those differences. So the high-level architecture is that we've got an XML repository or more, a number of XML repositories, a layer over that hides the access differences and the format differences. We have events that we can catch when things change within the repository. And we have constraints and relationships between the data that allows things to update themselves automatically. Now, you might think, this looks a bit like XForms. Well. So let me talk you through some of these elements and give you a bit more detail, and then having done that, I'll give you a few examples of how we're using it. So the central element of the system is an XML repository where we use elements for data and attributes belong to the system. So that's for the metadata about the data that's held in the elements. It's kept up to date with the devices bidirectionally. That means to say that if the device changes and sends new data, then the repository gets changed. But also the other way, if you change the data in the repository, that is how you control the devices, and the data gets sent back to them. And as a simple example, but I will give you more of these later, if you change the data value for the lights from a 0 to a 1, then the lights will go on. So then there's this thin functional layer around our repository that communicates with the devices. So they're actually plugins, so you just write one for a type of device or a particular format, and then that will work for anybody who wants to use that sort of device. They're responsible for knowing how to access the data from the device, obtaining it, converting it as necessary to XML, and sending back the data to the devices when that's necessary. We also allow one or more instances of the repository to talk. Again, I'll explain that a bit better later on. Then the events, so that's how we listen to, how we do the functionality within the system. We listen for events. The fundamental event is value changed. When a value changes, you can react to that in some way or another so that other things happen, so that other things can respond to it. We do have some other events, timer events in particular, and also events not only signaling a change of value, but also signaling a change of structure, such as insertions and deletions into the structure. we use a DOM model of events, so that means that the events bubble, so that even though they get sent to one particular element within the tree, it bubbles up, which means that you can listen to a whole collection if you want. If you're not interested in just one particular value, but the whole collection of values, you can put the listener at the collection level. And then the final element is the relationships, where you specify relationships between values so that if one value changes, that other values can be automatically changed to match. And that means that it may affect a device somewhere if that device is dependent on one of the relative values. So I don't have to explain to you what REST is, but it's of course the underlying mechanism of the web, and we operate the system once it's there and running. Everything is done using REST access to the device. So it's HTTP access using GET and PUT and so on. So let me now give you some examples. So I've already mentioned it. You could imagine a single bit called lights, which controls the lighting in a room or in a house. When the bit is 1, the lights are on, and when the bit is 0, the lights are off. But as I mentioned, it's a two-way relationship, because if you set the bit to 0, it switches the lights off. And there's another single bit. It says, "Is Jack home?" which, by the way, is not two-way. I'm glad one person got the joke anyway. There are two ways you can influence, specify relationships between values, and the first one is equality, which always ensures that the equality is always true. So, for instance, if I said lights equals Jack home, that means that whenever Jack is home, the lights are on, and whenever he's not home, the lights are off. Of course, this is not what you want, because he might want to sleep, and then he'd like to have the lights off. But that's all right, because we have another way of influencing values, which is the arrow, and that changes the value only when the value of the expression, in this case Jack home, when the value changes. So this means that when Jack comes home, the lights go on, and when Jack leaves home, the lights go off, but other things could happen in the meantime. So since this only happens when the value changes, that means that you can have what I've called here an override, but you can let other things control the lights as well. So for instance, you might have a switch on the wall, and of course that's just a bit in the repository. You switch it on, the bit goes to 1. You switch it off, the bit goes to 0. It hasn't yet specified got a specified functionality. We specify that functionality by saying the value of lights is the value that the switch produces, and again only when the value changes. So that if I switch the lights, the switch on, the lights come on. So the switch is now no longer hardwired to that function, so I can always change it. But it means that Jack, when he gets home and he wants to go to bed, he just has to switch the lights off, and they go off until he switches them on again. I should just say, as a side issue, I'm treating Jack home as if it were a single standalone value, but it's not. It's actually something more like this: home, people, person, name is Jack, present, or whatever. But just to make the slide simpler, I'm just calling it Jack home. Now, of course, you don't want the lights to come on when he comes home if it's bright daylight, but that's all right, because we have a sensor in the house that tells you whether it's dark or not. Of course, that has its affiliated bit in the store. So now we can say the lights have the value of Jack home and dark. So this switches the lights on if Jack comes home in the dark. It switches them on if he's already home and it gets dark. It ensures the lights are off when he leaves, whether or not they were already on and whether or not it's already dark. And it ensures that the lights are off when it gets light. So this simple statement captures all the requirements of controlling the lights, doesn't put them on when he's not there, and it doesn't put them on when it's not dark. Now, I should say we could actually combine those two into an equality, but the advantage of having those separate statements is that you get a form of modularity, because it means that you can more easily add other things or change the function of the switch without messing with other statements in the system. So although you could combine them, it's often handier not to. Now, how do we know if Jack's home? Well, he's got a number of things on him. He's got a phone which connects to the internet when he gets home. He's got a Bluetooth watch that can be picked up by some sensor at home. He's got a laptop that he switches on regularly. So you could say, well, Jack's home when we spotted the phone, and we've spotted the watch, and we've spotted the laptop. But of course, he may not switch the laptop on. So we could say, well, it's Jack's. We spot the Jack's phone or the watch or the laptop. But we've also seen, well, sometimes he might leave his phone at home. So what we actually do is we just count the things, and if it's greater than one, greater than one, then we assume he's home. So it's a sort of heuristic, but it largely works. Now, of course, he doesn't live alone. There are other people in the house. So we have a bit that just registers if anybody is home, and that's Jack and Jill and Jim. And we can say, well, the heating gets switched on if anybody is home. And here we really can use an equality, because the heating has required temperature as well as the actual temperature within the repository. So we don't need an extra override, because all we're doing here is enabling the heating, but not necessarily switching it on. But what it does mean, if nobody's home, it will definitely not get switched on. Now, one of the things we built is a door lock that we actually use at work for a project room that's openable with any RFID device. So when anybody comes along who's joined the project, we just let them register any RFID, whether it's their bank card or their phone or any other RFID device. We just register what that thing is, and then that gets them into the room. So opening the lock is really easy, because we just say the value of unlocked is whether the lock request, which gets saved whenever you swipe it, is in one of the allowed values. Now, to relock it, there are two possibilities. Either you want to toggle it so that you unlock it by swiping, and then later on you lock it again by swiping. Well, in that case, you just do an XOR between the current value and the request. Or the other possibility is that you want it to be opened with a swipe and then automatically lock a few seconds later. And there we use timer events. What happens is we unlock it in the same way, but when we spot, we listen for the event value changed on lock unlock, and if we get it, we dispatch another event init to the lock with a 2-second delay. So 2 seconds later, the lock gets an init event, and then it can reset the request value and relock the door. I should say this is how we currently do it, but we may change this in the future. We're evaluating different timing event mechanisms at the moment. So if you've got the Internet of Things and the only way you can get into your house is by swiping, then you're in a bit of a trouble if there's a power cut and no backup supply, and we can't do anything with that. But we don't want to have to depend on the Wi-Fi being up or the internet being up or the domain server being up in order to be able to get into your house. So we distribute these repositories over different devices. So actually, each device actually has its own copy of our system, but only for the local values, so that at least you can get into your house. So this means that there's no dependency on a central version of the system being up and running, even if the central version is where you actually do all the control. At least you can still get into your house. None of the data is visible outside the system unless explicitly revealed to somebody. We're building a mechanism so that Jack can expose the fact that he's at home without exposing how the system knows that he's home, and without revealing those details, for instance, his phone identity. So, for instance, he can tell the janitor of his building that he lives in that he can look to see whether he's at home, or anyone in the building, anyone who lives in the building in one of the other apartments, he can tell them how to find out whether anybody is at home, but that doesn't reveal any of the other details, like who it is that's at home, or again, how the system knows they're at home. So that means the janitor knows that he's at home, but he can't find out if Jack's actually down the bar if he's not at home, because there's no other details about him that's been revealed. Now, the advantages of using a state system like this, above the if this then that systems that are quite popular for Internet of Things, is that it makes the fine-grained access control much easier, because basically it's based on the containment of XML that you can reveal parts of the tree without revealing other parts. With an if this then that system, that would mean that every call would have to have some sort of mechanism for privacy. So it makes life much easier. So we're currently evaluating exactly which mechanism we're going to use. We've got a master's student doing a project for this. After the summer, we will have implemented it. Our current preference is for capabilities, but that's not yet implemented. So the UI, well, I gave a talk 2 years ago on this, so you can follow the link to see how we're using XForms to actually control this. Of course, XForms looks very much like the system. There's a very clear mapping between the one and the other, but it allows you to bind to values in the repository, display them on the screen in a readable way, and if you edit those, that changes the value in the repository, which has an effect of changing the devices. So it makes controlling the system very easy. So my conclusion, I'm reporting on something that's at early stages yet. We have our system that insulates us from the differences of the devices and the data that they use. It's running on Raspberry Pis. It gives us a very simple but very powerful mechanism for reading and controlling the devices. And we currently have 2 of these things running 24/7 at 2 locations, and a number of other ones that come up and down as we're testing it. If you want to play with it, that's the address. The slides will be online shortly after this talk. If you can't find the slides, you're in the wrong job. That's it. Questions?
Stephen, you talked about problems with power supplies, etc. So if things go offline and then come back on again, how do you resynchronize everything?
I mean, that's a good question. It's a regular synchronization problem. You know which one has changed, but in the end, the device, the state of the device is what rules. But if somebody's changed the value and hasn't been able to update it yet, the system hasn't been able to update it yet, then you wait for it to come back online and then update it. But it is a problem, and I can't say that we've got a pure answer to that yet. Yeah.
So how would you deal with codependent states? Like, for example, if the light switches on, if Jack leaves the house, he turns back, he notices the light is on, he enters the house again, and the light switches off. So the program is basically wrong. You have codependent states, which causes an endless loop.
Yeah, you have to program it right. That's true. It's a problem with switches that where you can't read the state, where the switch only sends a message to say, I changed state. So if you had a toggle switch, but that further isn't readable, then what that would mean is that you could switch the lights on, but you might have to toggle it twice in order for the system to get it. So, but that's more a hardware problem in the sense that you can't ask the switch what state it's in. So you would prefer to have switches where you could do that.
You mentioned the P in IoT.
Yeah.
And you mentioned the well, for
Yeah.
security. So you talked about something about privacy, and I wonder if you implemented something specifically for security, for updating these devices, for securely accessing the devices.
We haven't done it yet. I mean, for us, the privacy is the first and most important thing, which is what comes next. But we certainly intend to work on that.
Yeah. I think it's very important to
Absolutely,
these
you know.
issues, because that's often the forgotten things in IoT.
Yeah.
It is very important. I can imagine a scenario whereby it's Christmas Day and your cooker won't cook the turkey, and a message comes up saying, if you want to cook that turkey, you need to send $300. Right. Any further questions? Okay, thank you, Steve.
Thanks very much.